This is the video replication of the weekly preps for week 5 of the course Quantitative Analysis Applied Inferential Statistics. This week we'll be looking at a number of different distributions of random variables. The most important of these for our purposes is the normal distribution. The weekly prep questions for this week all introduce you to facets of working with the normal distribution. In exercise A, we'll look at standardized values, those that are converted based on the mean and standard deviation of a given distribution. Question 1 deals with a distribution that has a mean of 50. I've drawn a number line that is roughly symmetrical around 50. The distribution has a standard deviation of 10, and so, for example, 60 is one standard deviation above the mean, since 50 plus 10 is 60, and 40 is one standard deviation below the mean, since 50 minus 10 is 40. Similarly, 70 is two standard deviations above the mean, and 30 is two standard deviations below the mean. For part A, we're asked to convert a number of scores to standard units. The first score, 60, is here on the number line. We already mentioned that 60 is one standard deviation above the mean, so its standard unit is plus 1. Next, 45 is located here on the number line. This is halfway between the mean and 40, which is one standard deviation below the mean. So in standard units, 45 is negative 0.5. Finally, 75 is located to the right of 70, so in standard units, it is plus 2.5. Note that the value on the video itself is incorrect. For part B, we are dealing with the same distribution that has a mean of 50 and a standard deviation of 10. I've noted that 60, for example, is one standard deviation above the mean, as we discussed in the previous question. We're asked to find the raw scores of the following values in standard units. 0, the first value, will always be the mean, so its raw score is 50. To find the raw score of 1.5, we multiply the standard deviation, 10, by the standard units, 1.5. The product is 15, and 50 plus 15 is 65. To find the raw score of negative 2.8, we again multiply it by the standard deviation, 10, to get a product of negative 28. 50 plus negative 28 is 22. To solve question 2, we need to find the mean and standard deviation of the list of values first. We can rewrite the values in numerical order and then add them up to get a sum of 50. When we divide that sum by 5, the value of n, we get 10, our sample average, or x bar. We can write a second column containing x bar values for each observation. And then we subtract the mean from each observation. This gives us negative 3, negative 1, 0, 1, and 3. Remember that these sum to 0, so we need to square them to get values we can work with. The squared deviance values are 9, 1, 0, 1, and 9. These sum to 20, and we can use that value to calculate the standard deviation. The standard deviation is the square root of the sum of deviance values squared divided by our sample size minus 1. So we can fill in 20 for the sum of deviance values squared and 5 for n. 5 minus 1 is 4, and 20 divided by 4 is 5. The square root of 5 is 2.23. This is our standard deviation. Now, if you look in the book, you'll note that the answer to this problem is 2. Why is that? Recall that there are two ways to calculate the standard deviation. We calculated the sample standard deviation, which we noted is S, just a few seconds ago. However, if we calculated the population standard deviation, sigma, we would not include the degrees of freedom calculation in the denominator. That difference assumes the 5 values above are the only 5 in the population. This is the equation used in the book, and the population standard deviation is reported as 2. To finish part A, I'll draw another number line with the mean and 2 standard deviations above and below the mean. 12, for example, is 1 standard deviation above the mean. We'll identify the position of each raw score on the number line to work out the standard units. 7 falls halfway between 6 and 8 and is therefore 1.5 standard deviations below the mean. 9, the next value, falls between 8 and 10 and is therefore only a half standard deviation below the mean. 10 is the mean itself and therefore has a standard unit of 0. 11, like 9, is halfway between the mean and a single standard deviation above it, so it also has a standard unit of 0.5. It's positive, however, since it is above the mean. And finally, 13 is between 12 and 14 and is therefore a positive 1.5 in standard units. Finally, for part B, if you calculate the mean and standard deviation, you'll find the mean is 0 since the sum of these values is 0. You'll always find that the standard deviation is 1. This is always the case with standard units, something we can exploit for its predictability. I want to transition now to thinking about the area under the normal curve. When we used the number line before, we did not give much thought to the density of observations in the distribution. I've drawn an approximation of the normal curve here and marked the standard units both above and below the mean. This is roughly like the number lines we discussed in the previous section. What the table on page A104 allows us to do is estimate the number of observations that fall under certain points of the curve. For example, part A asks how many observations fall under the normal curve to the right of 1.25. So we'll mark 1.25 on the x-axis and shade in the area above it and to the right. I suggest doing this when you are just starting out. Actually drawing out the distribution and shading it in helps reinforce the logic at work here. But how many observations fall in the shaded region? We can look up 1.25 in the table, and when we do, we see that it has an area of 78.87. We'll round this to 79% for simplicity, and we'll keep rounding for the rest of this video. This means that 79% of the curve's observations fall between negative 1.25 and positive 1.25, the area I've indicated with arrows here. We, however, are only interested in the area to the right of positive 1.25. So we can take 0.79 and subtract it from 1, which gives us 0.21. This gives us the total area outside of plus or minus 1.25. If we were only interested in the right side of the distribution, we need to divide this number by 2, which gives us 0.105. 10.5% of the observations fall to the right of 1.25. Part B asks about the number of observations to the left of negative point 4. I'll mark this standard unit and shade in the appropriate part of the curve. In the table, we can see that point 4 is associated with the area 31.08. If we subtract 0.31 from 1, we get 0.69. The area outside of the range negative 0.4 to positive 0.4. Divide that in half, and we get 0.345. Or 34.5%. The area left of negative 0.4. Part C asks about the number of observations left of 0.8. Again, I'll mark the standard unit here and shade in the area we need to solve for. In the table on A104, we see that point 8 is associated with an area of 57.63. This is the area between negative 0.8 and positive 0.8. If we subtract that from 1, we get 0.42. Half of that is 0.21. But there is a twist here. 0.21 is only the area to the left of negative 0.8. And the question asks about the area to the left of positive 0.8. To get this, we need to add 0.21 to the area we found in the table, 0.58. That way, the value we're solving for covers all of the range of values to the left of positive 0.8. Those two values sum to 0.79, or 79% of the observations. Part D is slightly more complex. Now we have two parameters. Our area should be between 0.4 and 1.3. The area we need to solve for is pretty narrow and can't be as easily identified on the table. We'll start by finding the area associated with 0.4, which is 31.08. Remember that this covers the area between negative 0.4 and positive 0.4. So to get the area between 0 and 0.4, we need to divide this value in 2, which is 15.5%. The same logic applies to our upper bound here. The value associated with 1.3 is 80.64, but again, we only want half of that area, which comes out to be 40.5%. Remember that this covers the area from 0 to positive 1.3, so we need to subtract the portion of the area covered by 0 to 0.4 from that to get the area we're looking for. And this comes out to 25%. Part E is similar to the previous question, except that it includes 0. We can see this when we identify the standard units and shade in the area between. We'll follow the same process. The area associated with 0.3 is 23.58, and half is 0.12. This is the area between 0 and negative 0.3. The area associated with 0.9 is 63.19, and half is 0.315. This is the area between 0 and positive 0.9. If we add those two areas together, we get our answer, which is 44%. Finally, we get to part F. We're interested in the area outside of negative 1.5 to 1.5. I've shaded in both tails of the distribution now. When we look up 1.5 in the table, we see that it is associated with 86.64. If we subtract that from 1, we get 0.13, or 13%. This is the area covered by the tails. Finally, we'll address question 2 in exercise B. We can look these answers up on page A104. These answers, 1 for part A and 1.15 for part B, are identified by finding the area values in the table that correspond most closely to the given percentages.